Okay, well, I'm sure we still have a few more people that'll be filing in over the next few minutes, but let's go ahead and get started. So I'm Karen O'Neill, I'm the director here at Greenbank Observatory. And as always, I want to start off by thanking everybody for taking a bit of time out of your afternoon to learn about some very exciting science that's coming out of Greenbank Telescope. So today's community Zoom, we'll start off as always with a brief overview for me, just telling you what's going on with the observatory. And from there, we'll head into our primary presentation, which will be Emmanuel Fonseca, talking about the thermodynamic evolution of galaxy clusters. So with that, what's going on with Greenbank Observatory? Well, unfortunately, on the COVID side, things have not really gone that well over the last couple of weeks. Within the state of West Virginia, the number of vaccinated folks has gone up a little bit, but nowhere near the pace it was early on. So we're at about 53% of the state has now gotten at least one vaccine. And currently, the bad news is West Virginia has the highest number of cases daily that it's seen since the pandemic has started. So we are really seeing an uptick in number of cases within the state as well as within the county, as you can see here. Hopefully, this will turn into more people getting vaccinated and ease up our health systems a little bit. But that is the unfortunate news with COVID at the moment. On the positive side, though, all the staff here at Greenbank Observatory are either vaccinated or have a health or religious accommodation in place. So we're doing very well. Everybody is back to work again, and it's great to see friendly faces, although we get to see it all with masks on, but nonetheless still get to see everybody here. We still, of course, have our health checks in place as well to just keep an eye on things and to ensure that there's no spread of COVID-19 within the workplace. The telescope remains in full operations. This is actually our last week of summer inspections, part of our triennial inspection period. And so they're just, the inspectors are in this week, just kind of checking the last few things for their reports to go through. We're still working on painting the telescope and actuator repairs, and we're getting ready for our annual track inspection where we go through and we actually lift the top plates of the track, take a look at what's underneath, and make any decisions about repairs or changes that need to happen. As I've mentioned before, our Science Center has reopened, and we've got our bus tours and our exhibit hall are all open. Masks are required, as is advanced tickets are strongly recommended. Because we're trying to make sure that everybody is safe, we are limiting the number of people into the exhibit hall on the buses. And so we want to make sure that everybody gets their tickets in advance so you don't show up here and are unable to take a tour or visit the site. We also have our scientific visitors coming back on site, and that's been really nice to see, as well as some of our EPO visitors. And again, just nice to see things starting to return somewhat back to normal here. We've got the single dish school is also underway right now. They just, the people that are here just came down off the telescope. So this is the 21 single dish school with Arecibo Observatory as well. This year we're running it in hybrid mode. So we have participants both on-site and remote. We have about 15 on-site participants and about 40 remote participants. This is our first try at running one of these hybrid events with having people in both locations. We're hoping it goes well. It's certainly a path that we think will work well in the future to allow everybody to participate in single dish school as much as possible. Other things going on around site, we still have some job openings here on the engineering side, mostly software, digital, and mechanical engineers that we're looking for. And we also have an apprentice electrician job that's open here on site. Pretty soon you'll start to see our summer jobs for next year coming up as well. So I encourage anybody that's interested in jobs at Greenbank Observatory or knows somebody that might be interested to go and take a look at our careers website. We should have a data analyst position posting on there very soon as well. All right, so last thing I just want to mention is community Zooms coming up. These have been great. We thoroughly enjoy them. It's nice to see the community enjoying them. The next two community Zooms, as you can see, the one in 2 weeks will be with Steve Croft, looking at the breakthrough listen science. And then 2 weeks after that will be our own Dave Fair talking about gas and luminous infrared galaxies. So with that, I want to thank everybody once again for taking some time out of your afternoon and hand this off to Jay Lockman to introduce today's speaker. Thank you.
Thanks very much, Karen. Our speaker today is Emmanuel Fonseca from West Virginia University. And Emmanuel, why don't you just take over and share screen.
Sounds great. Can
Good.
you hear and see my screen?
Yes, and I'll read your title, Measuring the Radius of a High-Mass Neutron Star with Radio and X-ray Observations. And as always, if you have questions, please use the Q&A button in the lower right hand of your screen. Thank you.
Great. Many thanks to you, Jay, Karen, and everyone here in attendance. I truly appreciate the opportunity. As Jay mentioned, I'm now at the West Virginia University working as an assistant professor. Just started here a month and a half ago. So as you can tell from my office, it's just sort of been a whole lot of chaos and creation setting up here, but it's been fantastic. And I'm excited to one day in the very near future, when it makes sense to, and it's obviously safe to, be at GBO in person. It's been quite a long time. And there's just always been such terrific work going on there. Hopefully I'll make clear in this short community Zoom talk regarding some work of which the GBO has served as one of the key facilities in enabling the measurement of both mass and radius information of a fairly popular neutron star that we discovered and have studied over the last few years specifically. So just to give a brief introduction for those who don't normally think about neutron stars and specifically radio pulsars, pulsars, which are rotating neutron stars as shown in this video, were discovered in 1967-68 by Dame Dawson Bell Burnell. And it's one of the key ways in which we observe galactic neutron stars in general. So neutron stars have been known for some time to theoretically have these characteristic size and scale parameters, such as masses on the order of 1.5 solar masses and radii on the order of tens of kilometers or so. But the actual measurement of these two parameters has been observationally very challenging and nonetheless theoretically incredibly important for reasons that I'll go through in this talk. And like I said, one of the primary ways in which this is done is by studying radio pulsars with radio telescopes, such as the GBO or the 100-meter GVT. But nowadays, there's a lot of opportunities beyond the radio, specifically in X-ray frequencies, as well as even at gravitational, in the gravitational regime with gravitational radiation, where we can start to study neutron stars directly from a multifaceted and multi-messenger avenue. So in the radio, as I mentioned, radio pulsars have been known of for quite a few decades at this point, and it's through the timing of radio pulsars, so literally just measuring the arrival times, the times at which the radiation arrives at telescopes on Earth, and then studying how various variations in that arrival time data can vary over time. We can develop models of those variations that allow us to derive intrinsic properties of the system or pulsar in question, right? And these things could vary from variations due to orbital motion of the Earth about the sun, or in the cases of binary pulsars that have massive companions, a binary motion of that pulsar binary system, right? And so in quite a few cases, well, in a small but growing number of cases, so long as the measurements are precise enough and accurate enough, we can actually start to resolve not just the typical Keplerian motion, such as the orbital period, the projected size of the orbit, and so on. We can actually detect over time relativistic effects, so effects due to extreme gravity. An example of which is shown on the right, where you have an eccentric orbit, so an orbit that has a not quite a circular shape. And if the orbital parameters are right enough, over time, we'll actually see this shifting or precession of the orbital orientation over time. And this is one of the classic tests of general relativity, as was performed 100 years ago or so, to describe the orbit of Mercury, for example, which is observed to precess given its proximity. We see these things in pulsar binary systems, and we actually see them far more clearly to much higher and in more extreme degrees. And those by themselves, pulsar binary systems can be quite interesting for studying gravity in general, but in practice, we can also use these effects in pulsar binary systems to derive intrinsic properties of the system that you cannot gauge with Keplerian information. And specifically, I highlight here the masses of neutron stars, because according to at least general relativity, Einstein's theory of gravity, each of these effects, these what are called post-Keplerian effects, are dependent on at least one of the two masses of the binary components of the system. And so measuring one or several of these effects allows us to directly gauge that information, which has quite a lot of theoretical value. Now, like I said, recently, development of instrumentation for the study of neutron stars and pulsars and the X-rays has taken a sort of a meteoric rise, specifically with the rise of this fairly recent mission called the Neutron Star Interior Composition Explorer, or NICER, as shown here on the right, which is attached to the International Space Station, where instruments like this and future instruments for sure are sensitive enough to detect thermal radiation, X-ray thermal radiation from neutron stars and rotating neutron stars or pulsars that have relativistic signatures imprinted in their light curves. So when you see a rotating neutron star that emits X-ray radiation, you'll see a comparable X-ray pulsation. But in the X-rays, given that that radiation is typically emitted from the surface of the neutron stars, that radiation is heavily impacted by things like the compactness of that neutron star itself, which is a measure of both the mass and the radius. And so in those cases, theoretically, it is anticipated, if not expected, that those observables will have relativistic signatures that with some modeling will be able to tease out measures of radii and or masses as well. And very recently, a few years ago, the NICER team demonstrated this sort of endeavor by studying this isolated pulsar JO30 plus 0341. It's an isolated neutron star that's nonetheless very bright in the X-ray. So to make that clear, it is an isolated neutron star, has no binary companion, but NICER was able to demonstrate that they can nonetheless infer the mass and radius of that isolated neutron star from X-rays alone, which is really important and a testament to the work done by that team. So a couple of years back, on the radio time side of things, there was a discovery of a particular pulsar, JO740 plus 6620. It was actually discovered by none other than GBO's Ryan Lynch and company, who, as members of the GBNCC survey, published a study that analyzed a set of discoveries that were made at that time, this specific pulsar being one of them, and noted that the timing properties of this pulsar make it a great candidate for observing under the NanoGrav program. So for those who are not familiar, NanoGrav is the North American Nanohertz Observatory for Gravitational Waves, which is using an array of millisecond pulsars, so among the most precise and accurate pulsars known, to eventually directly detect gravitational waves. But the process of doing so basically requires us to study and characterize pulsar timing in general anyway. So there's lots of what's sort of called synergistic science that can be extracted by constructing this pulsar timing rate in general. And after about 5 years of timing or so for this specific source, JO740, we found that there were significant relativistic signatures in the timing of this binary pulsar, specifically the relativistic Shapiro time delay, which is basically a periodic effect that arises from the fact that the pulsed radio signal, as it orbits its companion, will traverse differing amounts of the gravitational potential of the companion. So what's shown here on the right is, on the bottom is sort of the expected theoretical delay due to that traversing of differing amounts of gravitational potential. So you get this delay where it cusps at a point called superior conjunction, so at the point of maximum delay. And as you can see, where if you eventually treat this effect with sort of a simple theoretical relation that's been vetted in the literature over decades, you can actually fit out this effect and through doing so estimate directly the mass and geometric information of the system, because the Shapiro delay is known to be directly related to those measures. So by measuring the Shapiro delay by itself, a team led by Hannah Thankful-Cromarty showed that we were able to find a very high mass neutron star. In fact, to date, it remains the highest mass known so far. And this was incredibly impactful work, beautifully led by Thankful, as shown by the large number of studies that have used and cited this result specifically. And again, all of these data shown here on the right are arrival times collected with the Green Bank telescope. So it's a testament to the GBT that this measurement was possible. And just to give you a sense of why measuring neutron star masses are important in general, here is a diagram of the phase space that's occupied by neutron star masses and radii. And each of these lines and curves in this phase space basically denote an idea, a theoretical model of what the interiors of neutron stars could be comprised of. And each of these lines differ basically in terms of the composition of neutron stars. Some folks presume differing amounts of, say, of sort of typical particles like baryonic particles, or even more exotic things like hyperons and so on, that are that are theoretically plausible, or people argue that they could exist, but have not yet been observed directly. But neutron stars in theory could house these things, right? So the idea is that each of these curves correspond to an idea of what the interiors of neutron stars can be composed of. So when we measure neutron star masses, we by themselves, they basically delimit one of these two sort of dimensions of the phase space. And these four sort of shaded regions at the top each denote a pulsar mass measurement made through radio timing. And this plot is not that old. It's only a year and a half old. But as you can see here, the mass measurement made with the GBT for J0740 plus 6620 basically lies at the very high end, the high mass end of this distribution. And the higher you go, the more curves you're able to basically rule out, because these bands correspond to the statistical uncertainties of these measurements. And as you can see, some of these curves, shown here in the lighter gray, are not able to intersect with these regions, meaning that each of these ideas are not able to predict high enough masses that would be consistent with the measurements. And so because of that, by themselves, neutron star mass measurements could be actually significant.
Emmanuel, we lost your voice.
Oh, can you hear me? No?
We can hear you, Emmanuel.
Okay,
you can hear me.
Yeah, thank
Okay.
you. We're okay. Thanks.
Okay, yeah, sorry for that issue. So again, by themselves, measuring neutron star masses can be very impactful, but it's only one of the two possible macroscopic parameters to measure for neutron stars. And because you only measure one of them in this two-dimensional phase space, you don't have the most robust constraints possible. And in reality, you would want points in this phase space, right? And so that's where endeavors to measure the radii of neutron stars comes in with huge importance. And so a couple of years ago, we were approached by members of the NICER team who notified us that there were ongoing and at that time, nearly complete observations of this source, J0740 plus 6620, in the X-rays with NICER. And they said, hey, we are likely to derive significant constraints on the radius, but those constraints could be much more substantially improved if we were to use the radio timing constraints on the masses, for example, as a prior information in our analysis. So that motivated us to revisit this source, incorporate additional data taken with the Green Bank telescope, but also to incorporate for the first time data acquired with a newly built telescope up in Canada called the Canadian Hydrogen Intensity Mapping Experiment. It's a project that I've been involved with since about 2015-16. In fact, if you look closely in this photo, here I am. And since that time, I joined the efforts to help build and construct not just the telescope, but the various instruments for it to conduct radio transient science, specifically studying known radio pulsars and observing fast radio bursts. But in a couple of years ago or so, I think about 3 years ago, we finally were able to make both instruments work, including the pulsar timing backend that allow us to observe pulsars with very high cadence. And in the case of J0740, we prioritize to look at that source basically once a day, every day. The way CHIME operates is that so long as the correlator for the CHIME telescope is on and streaming data, the pulsar backend will autonomously schedule things such that it'll acquire data for sources of interest. And for sources like the nanograph sources, which include J0740, we look at them basically as often as possible to support the various ongoing scientific projects. So with the GBT data, that's a growing data set as well as the CHIME data set, we endeavor to improve upon the various properties of the system that were known to see if we could meaningfully update those constraints and derive new things as well, such as constraints on the distance of the source, which would, in the study that was wonderfully led by Thankful Cromarty, we were not able to meaningfully constrain the distance at that time. But we were hoping that maybe we could with a slightly extended, far more dense data set. And again, data set of arrival times. So an example of that data set is shown here. So on the top panel is what's called the arrival time residual as a function of of observing year basically, or rather MJD, modified Julian date. And so each of these points here correspond to an arrival time measurement made on a different day. And the colors here denote the different basically receiver bands used. So the blue and green correspond to the GBT data at L band and 820 megahertz respectively. And these sort of goldish points correspond to the CHIME data, data acquired with the CHIME pulsar backend, which operates at 400 to 800 megahertz, so lower frequency than the GBT. And residuals here is just a fancy way of saying, you have your data set, which is the arrival times, and then you have a model of the variation in the arrival times. So if you take the difference with the data and the model, you get a residual. And the fact that the residuals are flat is a visual indication that the model adequately fits your data. And sure enough, the various common statistical methods to gauge goodness of fit and so on show that we get a really good, in fact, adequate modeling of the data in terms of the parameters we used previously, while adding a few others to describe other effects that are related to distance as well. And in the bottom, because we're using wide bandwidth receivers, where the observations are also themselves sensitive to effects due to pulse dispersion, which arise from the fact that pulses that travel through the cold tenuous plasma of the interstellar medium end up going a systematic delay as they traverse that medium, just due to the nature of the electromagnetic interactions. And because of that, we have to account for this delay, this dispersion delay, when we observe pulsars in real time. But the bottom plot shows you that there's actually a slight variation here over time. That's effectively, we can think of it as space weather, the fact that the number of electrons along the line of sight actually changes with time, and we can actually measure that quite nicely. And while it appears to be a slow effect, this is actually crucial for disentangling the Shapiro delay, because the Shapiro delay itself is, in terms of an amplitude, of order of a microsecond, of a timing delay effect. And these delays here as well are on a comparable order of magnitude. So it's really important to not just go for the effects that we want to, but also adequately model the effects that could get in the way of the measurements we'd like to make. And so finally, using methods that we had developed for the initial study led by Thankful, we revisited the timing effects that were previously analyzed in her work, in our work, and then we revisited that basically the same team, but including folks from the CHIME collaboration as well, to significantly constrain and improve upon previously made measurements. And so here is sort of what's referred to as a triangle plot showing our constraints with this combined data set of the various parameters of interest. So you have the mass of the pulsar here, which is sort of ambiguously called MP. MC here is the mass of the companion, which is a helium white dwarf, verified with external, very beautiful and external optical observations, which is itself a really nice study that shows a sort of a self-consistency in what's thought to be the evolution of the system over its lifetime, as well as the distance as well. And we are able to now measure the distance because we're measuring effects due to, say, the parallax of the system that we can gauge through timing, as well as apparent variations in several parameters that are believed to arise due to distance-dependent effects as well. So we now, for the first time, have constraints on both the mass, the geometric information here. This cosine of I is the cosine of the inclination angle of the binary system, as well as the distance to the source, which is itself inherently useful for things like energetics and so on, but was basically also useful for the subsequent analysis using these data by the NICER team. So various teams within the NICER collaboration went forth with these results shown here, using them as prior information for their analysis of their X-ray data, largely comprised of actual NICER observations supplanted with significantly with observations made with the XMM Newton telescope. And here is shown basically a video of one of the several studies made where they modeled their X-ray data and tried to pictorially get a sense of what they were seeing. Because again, what they measure are light curves, but light curves over a range of X-ray energies. And so what's shown here is the same physical scenario, rotation of a neutron star that has these what are called hotspots that emit the X-ray radiation, just at slightly different X-ray energies here denoted at the bottom left of each of these panels. And the aggregate effect is sort of shown here on the bottom left panel, showing what those light curves look like across the range of energies at which NICER is sensitive to. And again, this is just one of several studies that independently sought to make sense of the X-ray spectrotemporal data, so not just data in time, but in X-ray frequencies as well. Ultimately to, again, measure the relativistic signatures in their data, in the data that they acquired with NICER, so that they could ultimately constrain not just the compactness of the neutron star, which is a function of mass and radius, but then use the prior information to get at the radius of the neutron star. And so, as I mentioned, at least two different teams, one led by Cole Miller over at University of Maryland, another led by Tom Riley and company over at the University of Amsterdam in the Netherlands, independently use the data, use the constraints from radio timing, again, made possible by the GBO and CHIME observatories, took those data and information and used that as prior information for the constraints on the radius based on what was being told to them by the NICER data itself. And as you can see in these panels produced by both teams, we no longer have just a single constraint on one of the two dimensions, but we actually now have a significant constraint on the radius of the neutron star as well. So what was before this sort of infinite band, or at least like a band that was sort of limited in the mass direction, but not in the radius direction, with that information, we're now able to turn this into a finite region that allows us to say, which of those curves or equations of state, as they're called, are viable or consistent with the measurements made by both radio timing and the X-ray observations made with NICER. And as you can see here, these are the two different estimations of the allowed regions, or the posterior distributions, basically based on their independent analyses. And like I said, these are just two of quite a few works, at least for so far, of this one pulsar, J0740 plus 6620, made by NICER. I list them here. One study describes the observations themselves. The other two actually go for the constraint on the radius using the radio timing estimates as priors. And at least, and then another two here also go and use the information that they were to derive from that kind of multi-wavelength combined analysis to then make direct statements on the constraints on the radius, or rather constraints on the equations of state of neutron stars as well. And as you'll see, and as sort of shown here, this figure here shown on the right, which is available on the focus issue for NICER by the Astrophysical Journal Letters, shows you how the consistencies made by the independent teams agree. And there's general agreement. The differences arise from differences in modeling of the X-ray background information. And in that case, you're able to see that despite the independent avenues taken, there's general agreement on the constraint on the radius. And it's significant, by the way, which is really nice. So just to summarize, because I realize I'm a little bit over my own time, the J0740 plus 6620 is now one of only two neutron stars with a direct measurement of the radius, the other being J0030 that I mentioned earlier, also made with NICER. But J0740 is great in that it's at the high mass end of the neutron star mass population. So it provides a really interesting weighted constraint because of its placement in that sort of mass radius phase space. And again, just to reiterate, this was really made possible by the Green Bank telescope, the folks down at GBO, and most recently with CHIME, now that we're starting to incorporate that data into the nanograph pipeline. We're getting a nice multi-observatory constraint on all the things that make the system really interesting. And this work is not done. Again, there's only on the order of 40 or so measurements of neutron star masses with observations of pulsars. And while that might seem like a small number, realistically, each individual subsequent measurement has the opportunity to impact this sort of field pretty dramatically. So there's still lots of opportunities and lots of work ongoing to make measurements of neutron star masses, see if we can infer the radii with X-ray observations, and then combine all of that information for decisive statements on how the interiors of neutron stars operate. And a really nice avenue that's sort of arisen over the last few years is the fact that we have gravitational wave observatories operating now. And so there's just a lot of opportunity for synergistic multi-messenger opportunities in this front. And sure enough, LIGO itself has already put out a few interesting works regarding the questions of measuring neutron star masses, placing constraints on the equations of state of neutron stars, and using information derived from radio timing with observations made with the GBT to see if there can be sort of this truly synergistic way in which to constrain all that information. So I will stop there and I'll take a question or two. Forgive me for running over time, but thank you for the opportunity. I appreciate it.
Thanks very much, Emmanuel. If you have questions, please submit them in the Q&A box on the lower right. I noticed you have an NGVLA image up there, and this you expect to be, this instrument you expect to help with pulsar timing?
Yes, I mean there's timing going on now with the JVLA. It's producing beautiful data, and that's actually we're in the process of incorporating that into the subsequent nanograv data release. And so the NGVLA is expected to be even more important given its projected improvement in sensitivity and so on.
Okay. Other questions? We'll wait a minute to give people a chance to type in their questions.
No worries at all. And if there's a way in which I could, if folks would like these slides, I'm happy to make them available. Please do just let me know.
Then we have a question coming in through the chat. It says there was a proposal some time ago where the line spectroscopy of an iron line would be related through Stark effect to radius measurement. Do you know of any results on this proposal?
It's funny you ask. I recently came across this as well. Long story short, no, I'm not aware of any results on it. There could be, I just do not know, but I will look this up, and if you'd like, I'm happy to get back to you on it.
Okay. Well, we have a couple comments coming in through the chat window that I'll let you take a look at, Emmanuel. We don't see any open questions. Wait one more minute.
Yeah, no problem at all. And again, if folks have questions, you're welcome to email me. Forgive me if I partially was distracted because I actually have to teach in like a second, but I'll make
okay,
it
we'll let you go
totally
then.
fine. No, for sure. Sorry, that's why I was like, yeah, but no, I'm happy to stick around for another like half minute or so if folks have questions.
That's okay. Look, we'll bring this this webinar to an end. I'd like to thank everyone for their attendance. You can always contact Emmanuel offline if you have questions or comments. I want to remind you that 2 weeks from now, we have our next, the next webinar, which is Steve Croft talking about search for extraterrestrial intelligence, the SETI program at the Green Bank Telescope. We hope to see you all there. Thanks and goodbye.
Thanks, folks. Take care. Thank you.